you first learn about trigonometry, you learn about the trigonometric ratios. And the trigonometric ratios are these ratios defined for angles within right-angled triangles. So here I've got a little right-angled triangle, and that little angle there I'm going to call theta, Greek letter theta. And I've just defined some side lengths. So we've got the adjacent side length, the opposite side length, and the hypotenuse side length. And the trigonometric ratios were defined as things like sine theta is the opposite side divided by hypotenuse, cosine is adjacent divided by hypotenuse, and tan theta is the opposite side divided by the adjacent side, which also happens to be sine theta divided by cos theta. Now the problem with these is they, because they're defined in terms of an angle inside a triangle, a right triangle, they can only ever be evaluated for angles between 0 and 90 degrees. But the trigonometric values are really useful for angles that are different from that, angles that are less than 0, angles that are bigger than 90 degrees. So we need to come up with a way to talk about trig values for angles that aren't just the ones inside right angle triangles. So what we do there is we extend the idea of the trig functions to go outside of angles from 0 to 90 degrees, or 0 to pi on 2 if you're talking about radians. And the first step in that is to start working with a unit circle. That's just a circle centered at the origin with a radius of 1. That's why it's called unit circle, 1 unit. And we're going to work with that instead of just the right angle triangles. Now, but the first step in that is to link it with the right angle triangle definition. And so we'll do that by what we've got here is a radius going from point O to point P. And that's going to form a right angled triangle, that one there. And again, you can see my angle theta just like I had up here. So we're going to have a very similar situation first of all. We're just going to link the two visual ideas, the unit circle and the right triangle. So we've got that radius from O to P, forms a right angled triangle with an angle of theta formed with the positive horizontal axis. That's important. We'll always be talking about angles formed with the positive horizontal axis, just the positive side of it. A few other things you'll see in there is, it's a right angled triangle of course, the side that we used to call adjacent is now, if you think about that point P being at the coordinate xy, the adjacent side length will just be whatever x is. Similarly, the opposite side there, okay, you can see it'll be the same as that. So its length is the same as the y coordinate of the point P. Now because we've used a unit circle with a radius of 1, our hypotenuse side is going to have a length of 1 in this right triangle. Okay, so since that radius is 1, using our old definitions from up here for sine, cos and tan, we're now going to have that sine of theta is equal to opposite over hypotenuse, that's y over 1, or just y. Cosine of theta, that's going to be adjacent over hypotenuse, which is just x over 1, or x. And tan theta, opposite side over adjacent side, will be y over x. It's still sine over cos as well. Now these are exactly the same as they would have been in the old right triangle world. Okay, we've just defined them in a new way on this unit circle thing. And that's what we're going to take as our new definition of sine, cos, and tan. Okay, it's going to be an angle formed by a radius on a unit circle. Well, the sine and the cos and the tan of that angle are going to be defined as the y value, the x value, and the y over the x value. Totally consistent with the old way of doing things, but as we see in a minute, it's going to allow us to go outside of 0 to 90 degree angles, or 0 to pi on 2 radians angles. Okay, so let's start off. We'll start off with some angles in quadrant 2. Okay, so we're going to now move into an angle that's bigger than 90 degrees. It's gone past the vertical and it's sitting over there. So there's my new theta. And you can see already we're not forming a right angled triangle with theta because we've gone outside of that first quadrant. All right, so let's see how this works with things. Remember, we're going to keep our new definition for sine, cos, and tan. Sine being the y coordinate, cosine being the x coordinate, and tan being y over x. So a few things. We've now got theta between 90 degrees and 180 degrees, or pi on 2 and pi if you want to talk about radians. With our new definition, sine theta is y, cos theta is x, tan theta is y on x. And just note that they're going to be, sine theta is going to be positive because the y is up here. Cosine, though, is going to have a negative value because the x-coordinate is in a negative location. So then tan theta, positive over a negative, is going to be a negative itself. Now, how do we actually figure out what those values are? Because, I mean, we might know what theta is, but we don't know what the location that it goes to is. Well, it turns out we can use all those regular old values that we do know from back in quadrant 1 from the old trig ratio definition, because when you sweep this angle theta out, notice there's a little angle in here. I've called it alpha. You might not be able to see that very well. Alpha is the angle that's left over to get us to 180. This alpha is actually 180 minus theta, or pi minus theta if you're working in radians. Now that little angle does form a right angled triangle. You can see me tracing that out now. Okay, so there's a right angle right there. And if you just think about that right angled triangle, which I've reproduced down here, it's going to have side lengths of 1 on the hypotenuse again, still in the unit circle. The y-coordinate will give us that value there. And the absolute value of the x-coordinate will give us this one. Because remember, we don't want a negative length. So I'm going to take the absolute value of whatever that x is there. It might be minus 0.5 or minus 0.3 or something like that. So we want the absolute value of it. Now back to old trig ratios. The sine of that alpha will be opposite over hypotenuse, or y. Cosine of alpha will be adjacent over hypotenuse, absolute value of x. And tan of alpha is going to be y over the absolute value of x. Okay, so then comparing those with what we've got for theta, notice that it's exactly the same thing there. Sine is exactly the same. The cosine is pretty close. We got x up here and we got absolute value of x here. So it's actually going to be the negative of that one, because if we had to take the absolute value of it, we're going to take the negative of it. Tan of alpha, similar sort of situation. We're going to have y over the absolute value of x. So it'll be the negative of that one up there. So I've written that out down here. Sine of theta is the same as sine of alpha. So that means for a theta between 90 and 180 degrees, we can find the sine of that angle using the sine of that little alpha that exists in the 0 to 90 regime. Cos theta is going to be the minus of cos of alpha, and tan theta is going to be minus the tan of alpha. All right, so the key thing coming out of that is we can use all those old regular 0 to 90 degree trig ratio values to find the values of trigonometric functions for angles between 90 and 180 degrees. So something we couldn't do before when we could only work in terms of right triangles. So let's see, quadrant 3 works really similarly, except of course we're in a different place. So we're going to get different values coming out. So let's take a look. Quadrant 3, down here, we're now talking about angles theta like that. So they're sweeping out more than 90, more than 180, but less than 270. So between 180 and 270, or in radians, pi and 3 pi on 2. Using our new definition, we've still got sine theta is y, cos theta is x, and tan theta is y on x. This time, y is negative, so is x, but that means tan of theta, y over x, will have to be positive because we've got a negative over a negative. Okay, so that's something we're going to work through in a moment. Again, theta is not a right angle triangle angle. It's more than 180 degrees for starters. But you'll see that we do get this little angle alpha here, taking us back to the axis, the x-axis, which does form a right angle triangle. Okay, reproduce that over here. There's our little angle alpha. Again, hypotenuse is 1. Because I want positive lengths, I'm going to take the absolute value of the x-coordinate, absolute value of the y-coordinate to give me my perpendicular sides. And this time, that angle alpha is whatever our theta is that we're interested in, all the way over here. Take away 180 to give us a little bit left over. Okay, so here we're going to have, looking at our right triangle, sine of alpha will be opposite over hypotenuse, absolute value of y. Cosine of alpha, adjacent over hypotenuse, absolute value of x. And tan of alpha, the ratio of those two, of course, y on x. So in quadrant 3, if we compare our new definition and these little trig ratio values for that reference angle alpha, you'll find that sine of theta, this whole big one here, is going to be the negative of sine of alpha. Cosine of theta is the negative of cosine of alpha. and tan theta is exactly the same as tan alpha. So again, the same result, we're going to be able to use regular old 0 to 90 degree trig ratios to find us the values of 90 to 180 degree, and now 180 degree to 270 degree trig function values. Okay, so final quadrant, quadrant 4, so that's this one down here. Now we're talking about angles theta all the way around there, so it's bigger than 270 but less than 360, or if you like 3 pi on 2 to 2 pi radians. Using our definition again, same as our new definition always is. Now got this little reference angle here, alpha, which forms for us a nice little right angle triangle, reproduced here. Side lengths, x is positive again, so we'll just leave it as x. Hypotenuse of 1, of course, for a unit circle, and absolute value of y, because we're down underneath, y is going to be negative, so we want an absolute value of that. This time you can see alpha is going to be a full 360 degrees, but minus whatever theta is, so 360 minus theta. Looking at our triangle, sine of alpha, opposite over hypotenuse, will be absolute value of y. Adjacent over hypotenuse for cosine will give us x, and tan of alpha, absolute value of y on x. As we've done for the last two quadrants, let's compare those. We can see sine theta and sine alpha are just negatives of each other, because y is a negative value, and down here we've got the absolute value of that. Cosine of theta and cosine of the alpha, exactly the same value. Tan of alpha, absolute value of y on x, will be the negative of tan of theta. So you can see those three written out there as well. Again, all four quadrants now we can get the values of sine, cos and tan of angles in those quadrants using our old trig ratio values from quadrant 1. The only thing we have to do with them is every now and then one of them or some of them will be negated with a negative of the value. Okay, so putting that all together, you can see that essentially we can figure out the trig function values for any angle, okay, 0 to 360 and even bigger and smaller if you like, all just based on the values of the trig ratios even in quadrant 1. Okay, so we define sine theta to be y, cos theta to be x, and tan theta to be y on x. And then depending on which quadrant you're in, sine, cos or tan will be the sine, cos or tan of your reference angle in that quadrant, and sometimes with a negative and sometimes not. Now if you're thinking, how do I remember all of those, because there's like 12 different things on here I think, plus the different alphas, the different reference angles, there's a way we can write down a simple little thing. Notice that here it's the cosine that's positive. Here all of them are going to be positive because y and x are positive, all. Over here sine is the positive, and over here tan is the positive. So some people call this the cast diagram, C-A-S-T, tells you which quadrant, which ratio is going to be a positive value in. And then all you've got to kind of remember is which one's the positive and which one's not, or even just which one's positive, and what the reference angles are. Now the reference angles, it's always just going to be the angle between where your radius is and the horizontal axis. So there's our little alpha there. When we're in this quadrant, little alpha goes in there, and when we're in this one, our little alpha reference angle sits in there. So you don't even need to remember those formulas. If you like, you can just remember that it's always the angle that theta forms or has left over with the horizontal axis that's closest to where you are. Okay, so that's our little cast diagram. People sometimes make up little rhymes to go with those letters, but just make up something that works for you. The last thing that we haven't really dealt with though is what about angles which are exactly 0, 90, 180 and 270, or even 360. So the ones that sit on the axis itself. All the way through I've been talking about angles between the axes. We need to figure out what the values are on the axes as well. And it turns out these ones are actually pretty easy because you're sitting at places where you know exactly what the coordinate is. So we have our little unit circle here. If we're talking about an angle of 0 degrees with the positive horizontal axis, that's a radius sitting right here on the horizontal axis. So 0 degrees or 0 radians, that means we're pointing to that point right there, where our coordinates would be x equals 1 and y equals 0. And using our new definitions, sine of 0 degrees will be the y coordinate, 0. Cos of 0 degrees will be the x coordinate, 1. Tan of 0 degrees is 0 over 1 or 0. So pretty easy, that one. 90 degrees, that's where we'd be sitting up here. And that point's coordinates are, of course, x equals 0, y equals 1. So we have sine of 90 degrees is 1, cos of 90 degrees is 0, the x coordinate. Tan of 90 degrees is a bit of a weird one, 1 divided by 0, which is undefined. So we have no value for tan at 90 degrees. Moving further around, 180 degrees, so that's over here on the negative x-axis. There we've got x equals minus 1 and y equals 0. So sine of 180 degrees is equal to 0. Cos of 180 degrees is the x coordinate minus 1. Tan of 180 degrees will be 0 over minus 1. Finally down to 270 degrees, so we've swept out 90, 180, 270. There we're at a coordinate which is x equals 0, y equals minus 1. So sine 270 is minus 1, cos 270 is 0, and tan of 180 is again, dividing by 0, undefined. Okay. The last one, if you like, if you wanted to go back to 360, you're back at exactly the same coordinate again. Okay, so that means that the values of the trig ratios, or trig functions, sorry, for 360 degrees or 2 pi radians are just going to be exactly the same as 0 degrees or 0 radians. And it turns out that's what actually happens as you keep going. So if you went to an angle that's bigger than 360, you'd be repeating the same values because you are just going to go around to angles that you've already defined the trig values for. Okay, so these trig ratios are going to repeat themselves as you move around to bigger angles. On the other hand, they also repeat themselves as you go backwards as well. Okay, so we have this sort of repetition, periodic behavior is what it's called. Okay, so that's the trig functions defined and how we can find trig function values using our trig ratio values.